This episode is sponsored by Swagelok.
Managing hydrogen safely and cost-effectively while meeting performance benchmarks and reducing downtime is critical to building a sustainable clean energy future. That's why industry leaders trust Swagelok. With Swagelok, your team is a lot bigger. You have access to hundreds of fluid systems experts around the world who can keep you and your systems online and operating efficiently. Learn more at swagelok.com/alongside you.
Hello and welcome to the 1895 podcast, once again with me, Thomas D.
And me, Rob Cockerill.
And Rob, we're back again here and joined by a frequent guest on the 1895 podcast. We're delighted to have them back, and that is, of course, Swagelok.
We are indeed, but not such a frequent guest in terms of our actual interviewee today.
No, absolutely. Listeners will be familiar with Chuck Hayes. I'm sure he's been on the podcast.
A wealth of knowledge, I might add.
I want to say 5 times now, perhaps 4
possibly
times.
That many,
yeah. But it's great to have a new voice and a new face representing Swagelok on this one, and that's Buddy Damm, and we'll get into a conversation with him shortly, won't we?
Yeah, and we're reliably informed that Buddy has forgotten more than we'll ever know about this topic, so I very much look forward to diving into that.
Yes, and well, the theme for today is going to be alloy selection for fluid control components in hydrogen production environments. I don't know about you, Rob, but I'm glad that we have an expert on to discuss this topic.
I am as well. I mean, there are numerous aspects to consider when specifying materials for fluid systems in hydrogen production environments, but yeah, we really do need an expert to tell us all about that.
We certainly do, and well, with that introduction, I guess we should hand over to Buddy Damm, who is the Senior Scientist of Metallurgy at Swagelok. Buddy, thank you so much for joining us on the 1895 podcast. Perhaps instead of us reading chapter and verse about you, you could introduce yourself.
Yeah, thanks, Tom and Rob. Glad to be here today. So as you said, my name's Buddy Damm. I'm a Senior Scientist in the Metallurgy group here at Swagelok. I support a whole broad range of industries, but clean energy and hydrogen embrittlement are a couple of areas I'm very interested in.
Fantastic. And how long is it that you've been working in this industry, Buddy?
So I started my career at Timken and Timken Steel, and hydrogen is an issue in steel making and steel use. And did that for about 27 years. And then I worked for a few years at Special Metals, the makers of nickel-based alloys like Inconel. And hydrogen embrittlement is an issue and a concern for high-strength nickel alloys. And I did R&D to support development of those alloys. And now I've been at Swagelok for just under 3 years.
Certainly a lot of experience on this.
Yeah, I was just thinking that. So, Buddy, you must have experience across energy in the hydrogen space, as you said. I don't know, I'm thinking aerospace, semiconductors, those kind of industrial landscapes.
Yeah, fair bit of experience in oil and gas too, both in previous and current. So, yeah.
And when we talk about material science, what do those two words mean in actuality? Are we talking about the composition of the metals and the impacts of that on an application? What does it mean?
I like to think of material science as a mix up, if you will, of chemistry or chemical engineering, understanding the bonds and the nature of bonding, of solid state physics, so the atomic makeup of atoms and how they arrange themselves, and mechanics, so how do products respond to mechanical stresses, cyclic stresses, and that kind of thing. It's really a blend of a range of disciplines. And I like to say two things. One, that material science is really the oldest science. If you think early evolution of human beings making tools, they needed to choose the right materials. And then I also like to have a little fun and tell people that I've never metallurgist I didn't like.
Fantastic. And I like this, Tom. We're our 1895 theme. We go back to the history quite a lot. That was a great scene setter there.
A nice history lesson, and one that ties us nicely into today's theme, of course, which is alloy selection for fluid control components in hydrogen production environments. So, Buddy, what is the scope of fluid control components and how are they used within hydrogen production processes?
Yeah, so fluid control components are things like valves and regulators, fittings, components like gauges, and they're connected to the main production processes used during the manufacture of hydrogen. And they're really a crucial part of any industry. But in the case of hydrogen production, they're used for things like sampling or other subsystems to assure process quality control, and in many cases to improve the life of the components of the actual facility. So here at Swagelok, we engineer and manufacture these various fluid control components. And we also build specialty custom sampling or custom subsystems that people then connect to these various production units. We have an extensive global network of sales and service centers, and they work, the engineers in those facilities work closely with the factory experts and try and provide custom solutions to our customers. Really, our mission is to be fluid system experts that the world relies on. And so in addition to partnering to address things like materials of construction concerns that we're talking about today, our global network of support also helps customers manage things like flow path and process design to avoid things like dead legs or safety concerns, or to optimize efficiency and maintain sealing with small molecule gases like hydrogen. They also guide optimal design of sampling processes, so getting the right temperatures and moisture, improved sampling processes. And then they guide the product selection and systems design.
Oh, brilliant, isn't it, Tom, to get into that science, because we don't often get to do that. We spend so much time talking about the different pathways and the problems or often the challenges and opportunities, but to get into the science is great.
And that's what's great about these number of Swagelok podcasts that we've held over the last 18 months now, isn't it? Is really getting under the bonnet of these topics and digging deep into them.
Exactly, a masterclass. So Buddy, when we think about the key processes used to create hydrogen, it's mostly electrolysis and steam methane reforming, right? So we can spend a lot of time talking about the different shades of hydrogen, but it kind of comes down to those two. So let's talk about how the fluid control components come into play in those applications. If we look at steam methane reforming first, SMR, that is the dominant area. So what are the key process factors that impact material selection for fluid control components?
Right, yeah, so it's probably worthwhile to just do a brief explanation of the process as we go through. I think many of your listeners may know something about this, but SMR, as you mentioned, it uses methane or the methane in natural gas, along with a catalyst and pretty high temperatures on the order of 700 to 1,000 Celsius. And that process generates hydrogen from the methane gas, uses the oxygen in the system to break the carbon and hydrogen bonds. And one of the products that evolves in this process is carbon dioxide. That can be captured and sequestered, which helps reduce environmental impacts, but of course increases cost. So the process, the actual SMR reaction, again, happens around 700 to 1,000 C. The pressures are modest, 3 to 25 bar or 45 to 360 PSI. And the actual reaction vessels are fairly large and contain radiant burner tubes made of nickel alloys. The output of it is something called syngas, which is about 50% hydrogen with carbon monoxide and carbon dioxide. And there may be traces of impurities like chlorine or carbon or sulfur. So the fluid control systems at this point, especially sampling, they're not subject to those high temperatures, and so an appropriate high quality 316 stainless steel component works very well in this case, and allows the system to continue to be maintained. We at Swagelok have a special internal specification for our dual certified 316L, which includes a higher nickel and chrome content than the standard ASTM requirements, and that helps further improve things. In the actual process environment, in these large vessels with these nickel radiant tubes, the high temperature environment and the elements in the environment can cause damage called metal dusting, or you can also see oxidation or creep-assisted cracking. And being able to use these fluid control components to sample those gases and understand the content, the sulfur and carbon content, for example, allows you to determine when you may want to purge the system with nitrogen or steam, and that allows for improved life of the component. So it's really critical to the cost-effective operation of these things. After the initial SMR reaction, there's a water gas shift reaction that converts the carbon monoxide and water in the stream to more hydrogen. That process occurs at lower temperatures, around 180 to 250 C, and employs a catalyst and reacts the carbon monoxide and water. Pressures are a little bit higher than in the SMR reaction, on the order of 10 to 60 bar. But again, high quality 316 components are effective, cost-effective solutions there. That process fluid is then sent to a bank of pressure swing absorbers. Those separate the hydrogen from the other gases, and now as they do their job, they become saturated with those other gases. And so you need to run a recovery cycle on those units. And again, the sampling systems and subsystems associated with that allow for process control. And then finally, at the end, in all of these hydrogen generation processes or production processes, you gather the hydrogen and compress it for storage. Those higher pressures on the order of hundreds or even 1,000 bar now create enough stresses in the material to bring hydrogen-assisted fatigue or hydrogen embrittlement into the picture. And so at this point, a very well-designed component that is made for hydrogen service out of a high-quality 316 austenitic stainless steel is a very cost-effective solution.
Sure, and it's topics like that which make this so important for the industry, isn't it? And to make sure that innovators such as Swagelok are continuing.
Absolutely, we can only make it happen with those innovations.
Certainly. So if that's SMR, steam methane reforming, I'd like to move this conversation onto electrolysis, and we can start with alkaline electrolysis. What are the key process factors here that impact material selection for those fluid control components?
Right. Yeah. So in alkaline water electrolysis, the process takes advantage of electrochemical cells. There's a series of these electrochemical cells connected and referred to as a stack. And that stack is immersed in an alkaline solution. And the objective is to split the water into its component hydrogen and oxygen individual parts by applying an electric current. So the temperatures are modest, on the order of 50 to 90 C, and the pressures are also modest, on the order of 35 bar, 500 psi. But the solution is anywhere from 20 to 40 weight% potassium hydroxide or sodium hydroxide, and that solution is of that composition to improve the electrical conductivity of the solution. But it also generates caustic corrosion concerns for some of the components, particularly the low alloy steel components in the stack. Various subsystems are necessary in a AWE plant, and these things include things like sampling, purge systems, water and lye or caustic solution feeds, degassing systems, deoxidizing systems, and dryer subsystems. And in each case, the temperatures and environment are such that high quality 316 components make excellent fluid control components. In a few cases where the caustic environment is more concentrated, such as in the lye feed system, and particularly if it's being done at a high temperature, Monel or a nickel copper alloy, or also referred to as alloy 400, can be an appropriate choice, but really not needed very often, really special cases to be considered in each different application. In the stack itself, you have, of course, a series of positive and negative electrodes. So the negative ones are referred to as cathodes, and at each cathode, saturated water, hydrogen with saturated water is generated, and at the positive electrode or the anode, oxygen is generated, again with saturated water in it. At each of those cells, then those gases are collected. So on the hydrogen side, collection includes downstream things like separators and scrubbers to remove the lye and water and to purify the hydrogen. And at this stage, the system pressures aren't really high enough to be concerned with hydrogen embrittlement or hydrogen-assisted fatigue. But you do still have a corrosive environment with more moist caustic solutions. But 316 is a highly capable alloy in those environments. In some areas, you may have higher temperatures, again, and higher caustic concentrations, and Monel can provide a good solution for that. Further downstream of the hydrogen collection is, of course, the compression, again, like it was with steam methane reforming. So now you have to consider the stresses that those higher pressures bring and focus on hydrogen-assisted fatigue and hydrogen embrittlement. Well-designed 316 components are an excellent solution there. And then on the oxygen side, sometimes the oxygen is simply vented to air. May not be of high value, but in some instances, customers are collecting that oxygen and purifying it. And in those cases, you do want to be cognizant of and aware of material selection for oxygen service. So oxygen is a really powerful oxidant, and it can make things more easily ignitable. And there's some really important factors associated with that, things like pressure and compression rate, temperature, particulate matter in the stream, oxygen concentration, and flow path that all drive these risks for oxygen concerns. And again, working with our design engineers and field service engineers, you can try and mitigate a lot of these problems. But in the case of compression heating, if you have very rapid pressure increases, that can result in temperatures exceeding the auto-ignition temperature of non-metallic components like seals. Similarly, flow friction or flow at elevated pressures, typically above 500 psi, can generate heat that's sufficient to exceed the auto-ignition temperature. And then if you have particulate matter traveling at very high velocities, those can impinge on metallic surfaces and actually cause the metal to ignite in an oxygen-enriched environment. This isn't particularly likely in an electrolysis application, but always good to review the application carefully with the customer and make sure that we understand their conditions. In those cases, if there are significant concerns for oxygen service safety, you can use things like pure copper or nickel or alloy 400, Monel, and brass. But if that environment, that oxygen environment, has some alkalinity carried over into it, then you really need to avoid copper and brass and stick with nickel alloys or Monel.
Yeah, and we've seen this talking track emerging over the last 1 to 2 years, Tom. The oxygen collection from electrolysis operations. So that's very much a topic coming to the forefront. And again, it's good to know we've got the technologies and the expertise to support that.
Yeah, it certainly is. And I'm picking up on a lot of crossovers between conversations we've previously had with Swagelok, which tie in nicely to this conversation. So listeners should go back and listen to those if they have the chance. Buddy, one more, if I could. I'd like to ask about PEM electrolysis, or proton exchange membrane electrolysis. What are the key process factors there that impact the material selection for those fluid control components?
Yeah, PEM is very interesting technology, and here you use pure water as opposed to a caustic solution, and so some of the corrosion concerns go away, which is good. The proton conducting solid polymer electrolyte, or an ion exchange membrane, is used to enable the process. And temperatures are low, at least on the high end, are a little higher, from 60 to 300 C. Pressures are about the same, 35 bar or 500 psi max. And as with the alkaline water electrolysis, PEM also needs a range of subsystems for fluid control, for sampling, for purging, for water introduction, degassing, deoxidizing, and drying. And in all cases, the environments of each of those different applications, high quality 316 fluid control components are excellent, cost-effective solution. And as with both of the previous situations, downstream, as you're collecting the hydrogen and pressurizing it, those higher pressures now drive higher stresses in the components, and so hydrogen embrittlement needs to be taken into account. Components designed and made from 316L are excellent options. And similarly, if you're collecting the oxygen downstream, not venting it, you need to, again, be concerned with the same sort of oxygen service concerns that we talked about in alkaline water electrolysis.
Fantastic. Thank you for that, Buddy. Certainly really interesting to go through those, the various production methods, isn't it?
It is indeed. We've really got into the fundamentals of this kind of materials science and components today. Buddy, I guess, it sounds like although the initial material quality and the manufacturing is important to component longevity, finding a provider with materials science expertise such as yourself and Swagelok, and the ability to support customers in their material selection decision making can make quite a difference when building fluid systems that resist corrosion. Would that be, one of your key messages for listeners, one of your key takeaways?
Absolutely. Yeah, we really enjoy being a partner with our customers, helping understand their concerns and provide guidance in cases where they may not have the same experience that we have, and that partnership helps identify the most cost-effective solutions to improve long life of the components and very efficient processes.
Fantastic. Thank you for that, Buddy. And to wrap up this conversation, I guess if listeners want to find out more information on this topic, we could continue speaking about this for quite some time. But if they'd like to find out more, what can they do?
Well, we have a website that has some pretty good guidance on material selection. And of course, you can always reach out to your local Swagelok Sales and Service Center and get in contact with the application engineers and field service engineers that can help you in your initial design stage or any kind of troubleshooting. They always have a direct line back to the factory where various subject matter experts in a whole range of things, not just material science, can support that. And the subsystems, sampling systems and various other subsystems that we produce are often produced at those sales and service centers and then delivered and rapidly connected to these various systems and supported by our field engineers.
Wow, fantastic. Buddy, Tom and I are pretty much going to head off to the relatively simple science of committing this conversation to a podcast on the airwaves. But what's next for you today?
For me today, I have to do some work to prepare for a webinar on the effect of hydrogen on material performance for, again, H2View and 18.
Fantastic. Well, we look forward to that webinar, don't we?
Picking up the conversation again, yeah.
Yes, but
Yeah.
Buddy, thank you so much for your time and speaking to the 1895 podcast.
Yeah, thank you. Appreciate your guys' time, and thanks for the podcast, Tom and Rob.
This episode is sponsored by Swagelok.
Managing hydrogen safely and cost effectively while meeting performance benchmarks and reducing downtime is critical to building a sustainable clean energy future. That's why industry leaders trust Swagelok. With Swagelok, your team is a lot bigger. You have access to hundreds of fluid systems experts around the world who can keep you and your systems online and operating efficiently. Learn more at swagelok.com/alongside you.